Okay, we're going to talk about the concentration of ions in solution, but in particular, we're going to be talking about proton concentration and hydroxide ion concentration in solution. Water does something called autoionization. Now, your book is going to give you this formula right here where two waters make a hydronium ion and a hydroxide, but I prefer to use this equation right here. Water dissociates a tiny bit in itself. So what happens is it breaks apart to a proton, which we know is not naked in water. It makes the hydronium ion. It attaches itself to another water molecule and makes a hydronium ion. But it makes a proton and hydroxide in solution. If water is pure and at 25 degrees Celsius, room temperature, there's a steady state concentration of protons of 1 times 10 to the minus 7 molar. That's the same concentration of the hydroxide, 1 times 10 to the minus 7 molar. And because it's making a proton, it's an acid, and because it's making hydroxide, it's an acid, a very, very weak one, but it makes the same amount of acid and base, so it is neutral. But this is at such a tiny amount that, of course, water doesn't have enough ions in it to conduct electricity. And so this very tiny amount, this 1 times 10 to the minus 7, is very small. But water always has this in it. We have this happening in water regardless of where we find it. Now, again, the hydronium ion, many texts are using this in reactions, but chemists realize that a proton does not exist in water, and so they'll just say proton and agree with each other it's really a hydronium ion, and then go back to speaking about protons. But if you look at trying to understand the concept of acids and bases in water, it's a lot easier just to consider water breaking apart into a proton and a hydroxide. Now, if you prefer not to do it that way, if you want to look at it as a hydronium ion and two waters making a hydronium ion and hydroxide, then that's great. Go ahead and use the book to see all these things. But right now, I'm going to use this simple equation and just use a proton. It makes things a lot easier. Okay, proton concentration is important. Slight variations will kill things. In fact, if your proton concentration were to increase slightly over what it is in your body right now, you would get very sick. And likewise, if it were to decrease slightly, you'd get very sick. And so we are really concerned about measuring that proton concentration. We can measure it quite easily with an instrument, which you're going to recognize once I tell you about it. But it's very easy to measure, and it's very important. So what we're going to be doing is looking at proton concentration in water under various circumstances. To express that concentration, we put a bracket around the proton, and then that says proton concentration in molarity, and we don't have to put M after the number. Likewise, if I put brackets around the hydroxide, that says concentration of hydroxide in molarity. Just remember that proton concentration is the same as hydronium ion concentration, and so you can use those two terms interchangeably. At 25 degrees Celsius, we have that proton concentration and hydroxide concentration are equal to 1 times 10 to the minus 7, each of them. What we find is, because it's an equilibrium between water and protons and hydroxides, we find that if we multiply the proton concentration times the hydroxide concentration, that we always get this number, whether we modify one of these two concentrations or not. This means they're mathematically tied together. A times B equals, let's say if we say A times B is equal to 10, if I take A and say it's 2, you know exactly what B is. If I increase A from 2 to 5, you know that B must decrease. because when two things are multiplied by each other to equal them, they're mathematically tied together. This number, 1 times 10 to the minus 14, is referred to as Kw, the ionization constant for water. And it's always equal to 1 times 10 to the minus 14 at 25 degrees Celsius. And as far as we're concerned, everything's at 25 degrees Celsius. We're not going to worry about it being warmer or colder. So this equation right here, 1 times 10 to the minus 14 equals proton concentration times hydroxide concentration, holds true for all water, whether it's pure or contaminated with something, or that you purposely add acid to. Okay? What we do know now is that if proton concentration increases, let's say because you add an acid, well, hydroxide concentration is going to decrease. Or if we know one, we know the other by by algebra. So what we're going to do here is go through how do we figure out what is the proton concentration, also called the hydronium ion concentration, and the hydroxide solution of a 0.025 molar solution. Okay, first thing that we have to do is say, well, nitric acid is an acid, so it's an electrolyte. And electrolytes do what in water? They dissociate. So here's nitric acid. What is it going to make? It's going to make protons and nitrate. So if I have nitric acid in water, it's making a bunch of this. How much does it make? Well, if this is 0.025 molar, then the proton concentration must be 0.025. That 0.025 molar of nitric acid gives me that the proton concentration, or the hydronium ion concentration, is 0.025. And the nitric acid concentration is what? 0.025. Now, I know that I have proton concentration times hydroxide concentration is equal to 1 times 10 to the minus 14. If I know this, I know my hydroxide concentration. I can arrange that, and I can get that hydroxide concentration is equal to 1 times 10 to the minus 14 over proton concentration. I plug in my proton concentration, and what do I get? I get 4 times 10 to the negative 13. So now I know my proton concentration because my nitric acid gave me that concentration, and I calculated my hydroxide concentration because I know the two of these multiplied by each other give you 1 times 10 to the minus 14. So I can write proton concentration, or hydronium ion concentration, is equal to 0.025, and hydroxide concentration is equal to 4 times 10 to the minus 13. Go ahead now and try to do the same problem, but except for 0.001 molar calcium hydroxide. Notice that there's 2 hydroxides in calcium hydroxide. So when it goes into water, what is it going to make? 2 hydroxides in solution. Okay, first thing I have to do is write my equation to figure out what's happening. 1 calcium hydroxide is going to make 1 calcium and 2 hydroxides in solution. So if I have this concentration of the calcium hydroxide, it's gone now because it's been broken apart into this. What do I get? This concentration means that, of course, we have 1 calcium being made, so its concentration is 0.0010, but the hydroxide concentration is 0.00020. So I have this concentration of hydroxide. Now I can figure my proton concentration. Protons by proton concentration times hydroxide concentration gives me 1 times 10 to the minus 14. I can rearrange that, and I get proton concentration is equal to 1 times 10 to the minus 14 over hydroxide. I plug in my hydroxide value, and what do I get? 5 times 10 to the minus 11.